Welcome back, everybody. This is example 5.2 in our chapter 5 on forces and Newton's three laws. And this segment right here is just going to be on this example, so this might be a little shorty, but you're probably used to the longer ones, so this might be a nice little break for you. Okay, so what I'm going to do is I'm going to take this, we're going to read it, develop sort of a plan of attack, and then I'm going to take this whole frame and kind of squeeze it up into the corner so we don't need to waste all the space with it. So we got a pitcher throws an 0.15 kilogram baseball, which as I recall is actually the right mass of a baseball, accelerating it from rest to a speed of 90 miles per hour. All right. Well, there's a little bit of a problem right there because we're going to need to convert 90 miles an hour to meters per second. But not only that, but you have a from rest to a speed or to a velocity of this 90 miles per hour. That sounds like we have a change in velocity, and we have some kinematics going on, which we do because even though this is a force on, so this is a chapter on forces, which we equate a force, a net force, I should say, to being mass times acceleration. Acceleration is intrinsically tied to things like speed and a change in velocity and displacement. The ball doesn't immediately go to 90 miles per hour. He displaces it through a delta x, or displacement in the x direction, of 2 meters as he gets it up to that speed. So we have to solve for our force. So find the force exerted by the pitcher on the ball as he accelerates it from rest to this velocity through that distance. Okay, or through that displacement, delta x right there. So that's the idea. So let's take this and we're going to shrink it down, kind of put it up in the corner like that. All right, I'm going to see if I can lock that in place. There we go. And first of all, let's write down all the things that we know. All right, so the mass of the baseball. Mass of the baseball equals 0.15 kilograms. All right, accelerating it from rest to the initial velocity. Oh, this sounds like kinematics, doesn't it? It is. Equals 0 to a speed of, so V final is going to be 90 miles per hour. All right, let's just stop right there for a second. Do better, H. Let's convert that to meters per second. Okay. We're going to use our factor labeling right here. So what do we want to convert? All right, let's convert miles to meters. All right, and we know that, well, you may not know completely offhand, but we did talk about this. In 1 mile, there is 1,609 meters in a mile. All right, so that's our conversion from miles to meters, which we can use. So that may be a handy one to remember because we're going to be probably going to be converting miles per hour to meters per second a lot. Okay, so miles is going to go away, and hours. How do we convert hours? Well, 1 hour. I'll make another little bracket right over here. 1 hour is 3,600 seconds, right? 1 hour is 3,600 seconds, so hours in the denominator is going to get canceled out by that in the numerator right there. And we're going to have an answer in meters per second. All we need to do now is simply multiply across. Okay? So, what does this come out to? 90 times 1609 divided by 3,600. I get 40. Well, let's see. I only have two significant. I'm just going to go with 40. 40 meters per second. All right? 90 miles an hour, 40 meters per second. So that's going to be our final velocity right there after we've done our conversions and stuff like that. Okay? Well, not only that, but we also know that the ball has been displaced through a distance of 2 meters. So that's our delta x equals 2.0 meters. And we want to find the force. So what is a force? Or I should say, well, the force, it says the force, which is really the net force. It's the only force that is being applied to it. It's the force that's being applied to it from the pitcher. All right, so the net force is what we want to find right there. All right. Well, we know that the net force on an object, I'm having a hard time with my sigmas right here. Net force. A lot of times my sigmas look like backwards threes. It's just the way I draw them. Equals mass times acceleration. Well, we've got the mass of the ball. We need to find that acceleration, though. All right, what is that acceleration? We aren't given acceleration, but we are given things like initial velocity, final velocity, which we converted right here, displacement. We have an equation that relates all three of those with acceleration. So let's solve for acceleration first. All right, for acceleration, initial velocity equals 0 meters per second. Our final velocity is, after conversion, 40 meters per second. And our displacement equals 2.0 meters. Acceleration is what we want to find. Well, we know that final velocity squared equals initial velocity squared plus 2 times acceleration times our displacement. So our acceleration is going to be, let's see here. Move that up a little bit. We're going to subtract the VI over, right? So V final squared minus VI squared. And then that we're going to have just as a 2A delta. You know, I put delta Y. Sorry. We've most recently been dealing with motion in the Y direction. So 2A delta X. So that's all we're left with right here. So the 2 and the delta X are going to get divided down, right? So that's going to be 2 delta X in the denominator right there. And not a very good delta X. I'm having problems today. Delta X. All right. Well, that's what we can plug in to find our acceleration. Let's go ahead and do it. All right. V final squared is going to be 40 squared minus V initial squared. So that's just 0, right? Over 2 times 2.0 meters. All right, so it doesn't seem like very much in the denominator right there, but pitchers do apply quite a deal of force in a short distance of time. So that is going to be, this is interesting. You're probably getting a really big number. 400 meters per second squared. And that big number is going to be right. Because if you think about it, pitchers have to take that ball and they have to accelerate it to a really great speed in a pretty short distance. Those 2 meters isn't very much distance to bring it up to that speed. Which, by the way, is why pitchers' arms are constantly in ice when they're resting, or they're taking a few days off, or they're getting surgery, because there's a lot of acceleration they have to apply to that ball. So that's going to be our acceleration that the pitcher, at least this pitcher right here, is applying to the ball. Great. Well, let's just plug it in to our acceleration right there. We have our mass, and we can find our net force. All right. So the mass of the ball, 0.15 kilograms. Make a better point there. 0.15 kilograms times 400 meters per second squared. It's like 40 G's. That's a lot. All right. But the ball can take it. Probably the balls are used to getting bashed around by bats anyway. So what is that times? What is 0.15 times 400? That is 60 newtons. All right, and that's going to be our final answer. So it's quite an amount of acceleration. It comes down to 60 newtons, which is let's see, divide that by 4. That's like 15 pounds worth of force. All right, but it's applied in a very, very short distance, which is why it takes such a toll on pitchers' arms. So that's going to be our answer for example 5.2 on our pitcher, and net force and acceleration and mass. Well, thank you for following along, and make sure you ask me if you have any questions, and thanks for watching. I'll see you on the next one.